Y1, Y2, Y3, and up to 7. Okay, and you can see the value for the original image after you reduce the size by half or you rotate the image by 45 degrees, you can see all these 7 moments descriptors are almost the same. Okay, they are almost the same. Okay, so if you are interested in moment-based feature description, that's something you can look for. Okay, but this is not the purpose. Okay. So the one I'm going to introduce in spatial domain, okay, in spatial domain is so-called concurrence matrix, okay? And you will understand why it named co-occurrence matrix later on, okay? I will introduce two methods for co-occurrence matrix. The very first one is so-called the second order graph level statistic. Okay, you make a mark something, okay, after the title. This approach is used for structural texture. 它只用于结构式的纹路 ，OK， 只有结构式的纹路 ，OK。There are more than second order graph level statistic, but this is the most famous one, okay, second order, okay. Now the idea is we transfer a spatial domain into a so-called joint conditional probability function. Okay. Now this is the very first one I'm going to introduce. Okay. Here's the probability. Ij is conditional, which means it's given d and theta. Okay. This condition given d and theta. I want to know what is the probability in the image that you will see a graph level I changes to graph level j. Okay, so I and j are the graph level. So both are the graph value. Okay, so 第一个 ij 呢是灰阶值。Okay, I and j are graph value. What graph value? For some pixel location. Okay, for some pixel location at xy, that will change to what? Then j will be the neighbor. Is neighboring pixel. Okay, this is the current pixel. This is the neighboring pixel. So if this is xy, this given the condition. What condition? In direction. In the distance d. So d is the distance. It defines the neighboring point. Okay, and theta will be the angle, the direction. Okay, so that's it. So its neighboring point can be defined by what? So they got to be what? X plus cosine. I'm sorry. D cosine theta and y plus d sine theta. That's it. Okay? That's it. So that's how we define for every pixel point in this case, x1, x2, we find its neighbor, which is at the distance d, okay, with the orientation theta. Then you can find its neighboring point, and x2, y2, which has the value of j. Okay? So that's it. Okay. So which means if you have a texture like this, you are looking for a texture like this, then you should look for what? The theta. You should look for theta equal to 0 degree. Okay? Not any other degree. But if you have no idea at all what will be the texture direction in the image, maybe most of the case you will look for 0 degree, 45 degree, 90 degree, and 135 degree, which is the, right, that's the direction. That's this direction and this direction, and horizontal direction and diagonal direction. That's it. Okay? If you have no idea at all, usually we will look for these 4 directions. But if it's 0 degree, it's different from 180 degree. Maybe, I mean, this is 0 degree. If this is 180 degree, then you can look for another. This 8 direction. That's it. But if you just want to look for a texture like this, then you can make theta equal to 0. Okay, and look for what? Look for the distance d, if you know something about it. If you no idea about what could be the distance, for example, you might have some distance like this, and you might look for d1, and also for some distance d2. Okay? So it depends on what you are looking for or what you have for the texture. But anyway, this is the condition. Okay? So this is the condition. D give you the distance. And theta give you the orientation or direction. Okay? So for the user, you need to know something about the texture. If you know nothing, usually, as I mentioned here, you can look for this 8 direction or 4 direction. Okay, horizontal direction, vertical direction, and 2 diagonal direction. And you have no idea about what should be the neighbor, then you try out every possible. Okay, but for the given, so this is the condition. Okay, so this is the condition. This is the condition. That's what I'm saying. This is used for the texture description for structural texture. Okay, you only apply for structural texture. If you have a texture like this, then you should not go for this joint conditional probability because the direction is what? It's undefined, right? Or the direction could be in any orientation. So we need something else to identify the so-called statistical texture. Okay? So everybody follow me now? Okay? So this is the current pixel value at the pixel x1. And j will be its neighboring pixel graph value. Okay? Given the distance d and the direction theta. Okay? And this is the so-called joint. What is joint? Because you join I and j. I and j. Okay? Given at the direction. Now, think of this white paper, this white wall one more time. Okay, if we will look for, just assume we look for the horizontal direction. Okay, horizontal direction with any distance. What will be the value? Change from, every pixel might have the graph value of very close to 251. Yep. What will be its neighboring graph level? What will be the J? It got to be also 255, right? Basically, you won't see something else. But what will be the graph? If you have a white pixel value, 255, again, in the horizontal direction with some distance, what could be its neighboring pixel graph value? It could be 0. Or it could be 255. You know what I'm saying? Then the conditional probability could be different for the white wall or the white cell. That's the idea. Okay, that's the idea. To extract. I didn't say how to extract the feature yet, but we convert a spatial image into a joint. Why is joint? Because we look for I and J. Okay, not just look for X. This is a conditional probability for X. But when I say I and J, we look for the joint. Okay, the joint from I change to J based on what? Based on the condition B and C, the so-called the joint conditional probability. Okay, that's it. Okay, so it's simple. But you need to know some prior knowledge about the texture. If you have no prior knowledge at all, as I mentioned here, just try out every possible direction. Okay, based on the resolution you want, and also defines some possible distance. Okay, now let me skip a little bit. That's how we calculate the joint conditional probability. Here, H will be accumulative, okay, accumulative number of the pixel. That will change the graph value from f of xy to some value j, okay, based on its neighborhood f prime, y prime, okay, and f prime, y prime is just what I'm writing here is x plus b times cosine theta and y. So when you try out every possible value x, y, you scan the image pixel by pixel, right? Once you have x, y, you can always calculate x prime, y prime based on the given condition, which is the distance and the orientation. And then you just accumulate, see that? So H is the accumulation array, a two-dimensional accumulation array from change from graph value I to graph value J, right? So you just scan every possible pixel, then you can find out the number. Then you divide by the total number of pixels in the image, then you can get the probability. So it's so simple, just one line. What you need, just one line. Then you can convert the spatial image into a joint conditional probability given D and D. Okay, so if you have a four possible direction, then you just write down 4 lines. That's it. Then you can have 4 joint conditional probability. Okay, so simple, just one line. So don't make it complicated. It's quite easy to understand. Okay. Now, let's back why we call it co-occurrence. Again, the co-occurrence means we want to look for the co-occurrence from graph level I to graph level J. That's so-called the co-occurrence, 会共同出现的几率。And then why we call it matrix? Why we call it matrix? That's because we look for graph level I to graph level J. That will change from graph level I to graph level J. then 0. If for 8-bit display, then you have to look for up to 255. And what could be the possible outcome for J? Again, it's also 0, 1, 2, and up to 255. See that? It makes n matrix. You change the graph value from I to graph value J. And here will be the probability, or if we bring out H, that will be the number of count. You will see the graph value change from 0 to 0. So again, one more time, look at this white wall and this white ceiling. Now let's go back to white wall. What will be the probability? What will be the joint conditional probability that will present in the matrix? Well, since the graph value will change from 0 to 0, which is from black to black. No, you won't see, right? There's no black at all. So most of the value that could be very close to 1. Not exactly 1, but you know what I mean. You will see 1 here, very close to 1. You will change from 255 to 255 in its neighbor, which is divided by B and C. And most of the value will be 0. But for the white ceiling, you might see some might be changed to 255 to 255. Maybe you have a probability, I just make up, could be 0.7. But you might see some value from black to white, right? Or from white to black. That's another probability, right? Let me let's look more things, okay? From black to white, or from white to black. See that? Then we can extract the features from this matrix. That's the idea, okay? That's the idea, because the distribution will be quite different, okay? Now, let's back to the white wall, because most of the value will be very close to 1 from here. Now, and all others might have the probability of 0. So, name a major or name a feature that will show this characteristic for the white wall. Now, show me some of the major that can be used to identify this white wall texture compared to this white ceiling. Now, anyway, you learn from the very beginning of the semester. Remember what you have learned about thresholding? Right, threshold. But there's a lot of different thresholds, right? Just like your assignment number 1. You might go for the Osgood method, or you can go for... I'm surprised nobody used that for your assignment number 1.
Nobody?
You can go for entropy. Now, for this one, the entropy, the white wall, the entropy will be very close to what? To 0, because it's uniform, right? When I say the probability log 1 is 0.
Yes.
But for the white ceiling here, the entropy definitely is larger than the entropy of the white wall, because it's more complicated, right? Entropy, remember, entropy is a measure of complexity or uncertainty. So entropy is a good measure. So first we convert the spatial image into a joint conditional probability, and then we can find the features from this co-occurrence matrix based on the entropy or based on the power, blah, blah, blah. Okay, I mentioned that. That's the idea, okay? It's very effective, and the computation is quite simple. As you can see here, you just scan the image pixel by pixel, then you can find the corresponding accumulated joint value. Okay, change from graph value I to graph value J, and then divide by the image size, then you can get the joint conditional probability. Once you have the probability, then you can convert it or extract the features from it. Okay, that's the idea. Okay. I just mentioned here, usually if you just go for the 0 degree, 45, 90, and 135, then its neighbor is simply defined 0 degree just plus minus d. Okay, 45 degree, this is how we define its neighbor, 90 degree, 135, so it's so simple, okay, it's no big deal, okay. Okay, so that's it. So here give you the example, okay, suppose we have a 0, 1, and 2 are the graph value, okay? So if we have 1, 2, 3, 4, 4 by 3 image. Now, so here we'll recode from graph value 0 to 0, okay? Now, it's up to you. For our case here, we think of this, no matter it's 0 degree or 180 degree, they are the same. They are the same. Then in that case, then the value will becomes 2, because from 0 to 0 will be 1. And when we scan this pixel point, then again, its neighbor from 0 to 0 one more time, then we'll count all kinds of double count. It's up to you, okay? It's up to you. But for our case, we take 0 degree and 180 degree are the same. So in this case, the number of count will be 2, okay? And then we will have another, okay, from 0 to 0 or 0 to 0. So the total count will be 4. But for this point here, it's from 0 to 2, okay? So it won't be counted as from 0 to 0, okay? So that's how we get the covariance matrix, okay? Because the graph value we have so far is 0, 1, 2, and 3, okay? And this is the graph value of its neighboring point, okay? Suppose we set up d equal to 1, theta equal to 0, which means we scan horizontal line with 1 pixel distance, okay? So from 0 to 0, we have a total number of 4. That's corresponding to this, okay? 1, 2, 3, and 4, okay? Then you can look for from 0 to 1, that's 1, okay? 2, nothing else. So from 0 to 1, there will be 2, okay? So this is the number. Then we divide by the image size, then you can convert it into the probability. That's the idea for the co-occurrence matrix, okay? But again, this is applied for structural picture. You need to know some of the direction, or you need to present some of the direction, okay? Now, next, once you have the joint conditional probability, then we have to extract the texture features. The very first one is nothing but just calculate the energy, okay, for all possible graph value I, then for all possible graph value J, which is Pij, for the summation. Again, for this white word here, the energy, because we take the square, because most of the value will be 1 here, the square of 1 is still 1. Will be, what about the energy? What about the energy? What the white cell? Because all the value is less than 1. when you take the square, it will getting smaller and smaller, right? For example, 0.5. You take the square, then it will be what? 0.25. It will getting smaller.
Yep.
But when we take the square of 1, then it will be 1. So for energy, the white wall will have high energy. But for the white ceiling, the energy is much more smaller. Okay? Which means when you have a very complicated image, this energy value will be very small. Okay? The other one, as you say here, if you have a homogeneous or very regular or uniform image, then its corresponding energy will be very high. Okay? The other major, as I just mentioned, is entropy. Now, that's how we define the entropy, the probability times the log probability, okay, for all possible joint outcome from graph value I to graph value J, okay? Then, as I just mentioned, entropy is used to measure the complexity, okay? So for the white wall, the entropy will be very small. But for the white ceiling, the energy will be very large. Now, keep that in mind. You don't need to use both energy and entropy as the measure because they are highly correlated. Or you can say they are redundant. Energy 跟 entropy 事实上指的是一体的两面，不要两个都用，因为那是浪费了，而且呢会造成一些不必要的困扰。Because when the energy is high, the corresponding entropy must be very small, and vice versa. Okay? For entropy, if entropy is large, then the corresponding energy is small. So just pick up one. Which one you want to measure homogeneous texture, then you go for the energy because it's large. Okay? But if you want to look for a very complicated texture, then you might use entropy. Okay? So depends on which one you try to find that will return the maximum feature value. But don't need to use both because they are redundant. 它们是重复的. Okay, so you can go for the energy and entropy, or here's another definition, is based on the inertia. Inertia is what? The difference of graph value from graph value I to graph value J, the difference. Then times the corresponding probability. That's it. Okay? So, again, the inertia for the white wall will be very small, right? Because most of I will equal to J, right? In its neighbor. But for the white ceiling, the difference could be very large because we are changing from white to black or black to white. So we don't care about the sign, we take the square. So again, inertia is some measure, okay? Not just based on the probability, but based on the outcome difference. So that's called inertia, okay? That's inertia. Or if you want to emphasize the local homogeneity, then it's divided by the difference. So again, C and D, they are redundant. You don't need to use both. When C is small, D definitely will be very large because it's divided by the square of the difference between I and J. But for this one, we take the square of the difference. Okay? The only difference, why is plus 1? Because we try to prevent what? Division by 0. That's it. 加一唯一的目的是避免除以零. Okay? We cannot divide anything by 0, right? So we plus 1 here. That's the only reason. So basically C and D are the same. They are the same. But again, if you want to try to emphasize the large value, or you try to measure the local inhomogeneous, then you look for inertia. You want to look for the local homogeneity, then you use D. Okay? That's it. Or you can find the correlation. Okay? You can try to, just like the normalized cross correlation, exactly. Because if I and J are highly correlated, then this correlation value will be very high. Okay? Which means what? If I is large, then J is also very large. Okay? Which means they are highly correlated. Now the definition just exactly like the cross. Okay? Normalized cross correlation. Here, this is the covariance, right? The first term here, the covariance. Then divide, or we standardize by the standard deviation, okay, for I and for J. That's it. Okay. So that's another measure. So it's basically the same. Here's some more entropy related feature. You can go through all the details, but here I only want to introduce the very last one. Okay, the information measure. We calculate the entropy of X. Suppose we have X and Y, variable X and Y. We calculate the entropy X and entropy Y, and also the cross entropy for X and Y. Here. Well, anyway, that will be the topic of my next semester class. Okay, but just know the result. If X and Y, that's it. If for our case here is I and J. Okay, if I and J, the graph value I and J. If they are independent, when we say or when we can prove X and Y or I and J are not correlated, the correlation coefficient is 0. It doesn't mean they are independent. Okay? Anyway, you want to know, we'll talk about that next semester. Uncorrelatedness is only a necessary condition of independence. 我们说两个变数是独立的，不代表，纵使两个变数它的相关系数是0，不代表它们是独立的。非相关性只是独立性的一个必要条件，可是不是充分。But anyway, if I say X and Y or I and J are independent, it means what? The joint probability that you can observe I and J at the same time will equal to the multiplication of the marginal probability for X and Y. If I say they are independent, it means what? Whenever you look, you know something about I, but you cannot estimate what could be the outcome of J. Just like when you roll a die. Okay? You roll a die. When the outcome equal to 1, what will be the outcome for the next toast? You have nothing. I mean, with this information at the current outcome won't help you to make the estimation. That's so-called they are independent. So when I say if X and Y or I and J are independent, which means the joint probability will equal to conditional probability. So here's another measure. Okay, so that this is called the mutual information. Mutual information. Okay, mutual information. Talk too much. So anyway, mutual. That's another major information. Okay? So we can calculate Hx. Hx is what? Is P of x times log P of x. This is the entropy, definition for entropy, right? Okay? And then you can calculate the entropy for Y. Okay? And then the dashed line here, okay, this is the joint entropy, okay? So it's right here, the joint entropy. Joint entropy, then they are truly independent, then the joint probability can be written down as the multiplication of the marginal probability of Pi times Pj, okay? And the intersection part is the so-called mutual information, okay? So if there's no difference between I and J, the mutual information will be equal to 1. No, I'm sorry, it will be very large because they overlap to each other. But if I and J, they are truly independent, then the mutual information will be equal to 0 if they are truly independent, which means there's no common information at all, okay? In this case, what? The texture must be very complicated. I didn't say the white cell will have the mutual information of 0, but the mutual information from here, from graph value I to graph value J will be very large, right? Once you see the white pixel, you will know, oh, its neighbor got to be also white. But when you look at the white cell in here, if you look at a white pixel, its neighbor could be black or could be white. So the mutual information could be lower compared to the white wall. 这个叫做 mutual mutual 是共同的共有的 Okay, so let me say one more time. If two variables x and y, in our case is graph value I and its neighbor graph value j, they are truly independent, then the joint probability will be the product of the marginal probability. And this is how we define the mutual information here, okay? This is how we define the mutual information. The entropy of x plus entropy of y and minus the joint entropy of x and y. That's it. It's called. So mutual information is another measure, okay, for the texture complexity. Okay, that's something. And if you want to know, because I put a lot of 1 and 2, but basically they all based on the entropy of x, the marginal entropy x, marginal entropy y, and the joint entropy sy. Okay, and if they are truly independent, this must be true. Okay, this must be true. That's it. Okay, that's all you need to know. Okay, okay, you can based on the covariance matrix, you can design your own. Okay, that's like Okay, based on this concurrence method, you can design your own. Okay, you can design your own. But that's the good thing about how you convert a spatial image into a joint conditional probability. But remember, it's only good for structure texture. Okay. Now, here's some other way. I will skip it. Okay. I will skip this one. It's based on the wrong length, but basically it's applied for structure texture. Okay, but once you know this joint conditional probability, that will be good enough. Okay, so I will skip that. Okay, the next one I spent too much time. The next one I'm going to introduce is called neighboring graph level dependency statistic. Now, put a note here. It's for statistical or random texture. Okay? It's for random texture. The random texture is something like the surface of the table, okay, of the desk here. Okay, 随机纹路啊，这个是给随机纹路。So it just look for the neighboring. It does not look for the direction because it has nothing to do with the structure. Okay, because all the texture will appear randomly. So just like the white ceiling, it can be categorized as a statistical texture or random texture because you cannot see any direction, right? You cannot see any direction for the dark point, okay, on the ceiling here, right? It is a so-called statistical texture. So for that, we don't look for the direction, but we just look for its neighbor, or its neighbor, okay? So in this case, we only need to define the radius, the distance, but we will look for all the direction. That's it, okay? So, and then you will come up with this joint conditional probability one more time, okay? Then we will finish this concurrence method. Very well known, very famous, very popular one. The good thing is you can design your own. You can design your own joint conditional probability. And then you can design your own feature descriptor from the concurrence matrix. Okay, that's the idea. Okay. Okay, and don't forget to hand in your assignment number 3. Okay, thank you.